In this video, we're going to look at a quick review of statistical quality control, SQC. So far we talked about quality in general, total quality management, and of course this area is a very important aspect of quality management. So what is statistical quality control? Well, essentially what we observe is that all output comes from a process, and in a lot of cases the output from the process is random. And so if we were to draw the variation in the output from the process that is fairly stable, in most cases the output might look something like this. It could be a normal distribution with a mean, mu, and standard deviation, sigma. And the idea is that if we look at variation, then variation, that should be V, in the output can come from two sources, what we call common or natural causes. Basically that just means that every part that goes through that process, every item, is subjected to the same set of conditions, or what we call assignable causes. Right? So what statistical process control involves is trying to discern between what are common causes when we observe variation versus assignable causes. Now, on the normal variation for a process, we would expect that the variation to take place between plus or minus 3 standard deviations, or in other words 6 standard deviations, 3 on either side. All right? And in that case, we would expect 99.73, I believe it is, % of all of our values to occur in that range, 6 standard deviations. But when values occur outside the range now, we view those as outliers. And those outliers is what tells us that something is wrong with our process. So when a process is stable, if we observe the output, and as long as the output falls within the appropriate ranges, then we're okay. But if we then find out that the values fall outside of the range, then we have an issue. And that brings us, if you recall from your statistics, it brings us to the topic of hypothesis testing. If the process is in control, they would expect the variation to occur within that range. When we have very extreme variation, that means we fall outside of that range, so that's sort of extreme and outlier. That causes us to re-examine our null hypothesis. And so essentially what the hypothesis would look like is I would say HO, if you remember from your statistics, which would be a null hypothesis, is that the process is in statistical control. Alright? Versus H1, which is your research hypothesis, the process is not in control. So when do we find evidence to support H1? Whenever we have outliers. And outliers are so extreme that the process cannot be in control. And so that's what we look for. So we have we typically consider different types of variation, but one of the things that we consider is the variation of the mean, or the process mean. In other words, we expect a process to have a certain average, but that average could change over time. So let's just say we start off here. Well, over time, that could change. Mu2, or it could be getting, mu3 and so forth. That process average could change. So when we are monitoring our process, we want to ask, is mu still the same original mean? In other words, has things changed, or is it pretty much the same? So the average of a process can change over time, and we want to be able to detect that when that happens. Another thing that could change is that the variability of a process. So just consider this case here. What if this is our process variation, sigma? So this is what we're seeing as our variation right now. Well, it's possible for us to begin to see something that looks like this. Whoa, if you check that out now, we have a lot more variation in this case. Or what if it actually came a lot smaller? Then something is happening here. The range of the process is actually changing. The mean could still be the same, but the process variation is changing. All right? All of a sudden we start to see wider and wider swings. So we want to be able to detect that as well. So what do we use for those? So statistics allow us to basically calculate ranges. Really, that is an application of confidence intervals. So if we think about means, for example, if we take a number of samples and each of them have a sample mean, then we would expect the mean of all of the means, right? If we were to take that and add plus or minus 3 standard deviations, then we'd expect 99.73% to fall in that range. So anytime we get a sample mean that is outside of that, we have an issue. So what we tend to do is we create a control chart. We say, here's where we think the mean of the process is, and these are the limits. So this would be for example, your mu x bar plus 3 sigma x bar, and your mu x bar minus 3 sigma x bar, right? And so we would monitor the process like this. And if it so happens that it falls outside that range right here, then that is an alarm for us, because we're now getting into the zone beyond 3 standard deviations, and so therefore that is a problem. All right, so that is called an X-bar chart, and that X-bar chart allows us to monitor the process mean. Now with the X-bar chart, in a lot of cases we really don't have the information to calculate the 3 standard deviations that we have right here. So let's just see here. If we really can't always find that 3 sigma x bar. So we have a way of estimating that in a table by a formula called A2 R bar. A2 is just a factor, and R bar is the average of the range of the data that we collect. Because what would happen is that typically we would take samples of data at specific points in time, and each sample would have a number of observations in it. And so, for example, let's just take a look at one sample. So if we had a sample taken at a given point in time and it had 5 values in it, x1, x2, x3, x4, x5. All right. So R bar is essentially would just be, we would need to calculate, before we could find R bar, the range of this sample. So we would have to take the range of this sample, let's call it sample 1, would be the maximum value minus the minimum value. So if I repeated that that's just one sample. What if I took another sample, sample 2, and I got 5 values? Then I get an R2 and an R3 and an R4, etc. I could take these 4 values, add up all of the R's, the ranges, and divide by the number of them that I have, and that gives me R bar. So with this average range, and once I know the sample size in this case, which is 5, there's a table in our text that gives us a value, a factor for A2, and if we calculate the average of the ranges, then that is our estimate of 3 standard deviations. But we also need an estimate of mu. How can we estimate mu? Well, if you look for this sample right here, I would calculate a sample, let's call it x bar 1, which is the average of those, right? And if I repeated that for each sample that I took, I would have x bar 2, x bar 3, x bar 4, etc., etc. So if I took the average of the averages, I get x double bar is the sum of x bar I over m, the number of them that I have. And then I put those two pieces of information together. So now our x bar chart is calculated as follows: x double bar plus or minus a 2 r bar. So that is our estimate of mu x bar plus or minus 3 sigma x bar. And we use that to get our limits like we did over here from sample data. And then we will simply continue to monitor the averages from future samples. And as long as the averages from the future samples fall within the range, then we're okay. But when it falls outside of the range, then we have to stop the process, check to see what's wrong, because there's an assignable cause, make that correction, and then continue once the correction has been made. Okay, so that's how we kind of are using statistics to help ensure that a process conforms to the specifications that are required. So we just talked about the X bar chart. Well, if we wanted to control for process variability, and as I mentioned to you, that if we would look at if this line represented the mean of the process, it's possible to see this kind of variation, but it's possible to start seeing it increasing. So the process is actually varying more and more. So this could be mu, but as you can see, the standard deviation is changing. So how do we monitor for that? I've already mentioned the idea of the average of all of the sample ranges. And so if we have R bar from, say, M samples, in case you're wondering what I'm talking about, what would happen is that we would take samples 1, 2, 3, 4, etc., however many samples, and we'd have observations 1, 2, 3, 4, 5. So this would be like if x11, this is the row, so x21, x31, x41, x51. What that means is that this is my sample 1, and this is the first observation, second observation, third, fourth, fifth. So my sample sizes n is equal to 5, but my number of samples could be 3, 4, or whatever. And so each of those samples would have a range, and each of them would have an average, right? So the average of these values would give you x bar 1 for sample 1, x bar 2 for sample 2, x bar 3, x bar m, and then we would have r1, r2, r3, rm, and if I average those over here, then I could get r bar, and if I average those sample means I could get x double bar. All right, so once you understand that, so r bar would be obtained here depending on the data that we have. To set up control limits now, we could set up control limits as follows. This would be r bar, this would be d4, this is a factor that we get from a table, and that table is available in our text. d4 r bar and d3 r bar would be ours. So this would be a lower control limit, your upper control limit, and your average. Again, every time we take a sample and we identify the range, we simply plot it, and if we see one of the ranges fall outside, then we know that we need to stop the process. Something is wrong. The process is now out of control. Okay, so that is another example of a control chart, but this controls the process variability. I want to mention one more chart, actually two more charts for you. those two charts that I just discussed, which is a range chart, an R chart, an X bar chart, controls what we call variables. And variables are things that we measure. We measure them. So we could talk about distance, we could talk about weight, height, etc. And we do that. But if we talk about attributes now, those are things that we count. We count them. How many red shirts in a room? How many blue shirts in a room? You know, how many short people, tall people, etc. So in a case like that, we have two types of charts that we talk about. One is called a P chart, which is for proportion defective. It's related to the binomial distribution, and so we could talk about something is either defective or non-defective. So usually what we have is n, a sample size, x, the number of defects, and p is x over n. Once we get that, if we take several samples, then we could create p bar, which is the sum of all of the sample proportions divided by the number of samples that we have. And I'm sure you may recall this, which is a confidence interval for proportions from your statistics, p bar 1 minus p bar over n, where that now gives us a set of control limits for controlling proportion defectives. So if you're producing, say for example, light bulbs, and you're going to sample 50 light bulbs at a time, once you compute from some historical data the limits, your upper control limit would be here, which is your p bar plus 3 standard deviations, 3 sigma p, and then your p bar, which is your mean, and p bar minus 3 sigma p. This is your sigma p right here. Alright? And again, same idea. You plot, if you go out of the limits, then there's something wrong with your process. So if you recall your statistics, this is just a confidence interval for proportions. And last but not least, we're going to talk about, there's another chart that deals with attributes. It's called a C chart. C chart. This is a case where we monitor the number of defects per unit of an item. So how many scratches in a paint job on a car, or how many kinks are there in a yard of wire, things of that nature, how many typos on a page. In a case like that, what we monitor is for each sample, we'll call it C. Ci would be the number of defects in a sample. So if we get the number of defects, if I then take the average of all of the defects in all of the samples, if I have m samples, then I get C bar. And the interesting thing about this kind of distribution, while the proportion chart is based on the binomial distribution, this chart is actually based on a Poisson, P-O-I-S-S-O-N. And the thing about a Poisson is that the mean and the variance are the same. So in other words, mu is equal to sigma squared. So because the mean and variance are the same, therefore the standard deviation is the square root of the mean. So what happens now is that our chart is now C bar, that's the mean, plus or minus 3 standard deviations. 3, well, what's the standard deviation? The standard deviation is the square root. Remember, this is variance now. So if I want standard deviation, I must take the square root of mu. So sigma is the square root of mu. In this case, what is my square root of mu? My estimate of mu is C bar. C bar. And that gives us a chart that we can use to control the number of defects per unit of an item. Okay? Now, one of the nice things, as I mentioned, is that XLOM, if we could do this stuff manually or in Excel, but XLOM allows us to do those relatively easily. So if I were to just simply go over to XLOM, we could see here quality control, and we have the P charts, we have X bar and R charts, we have C charts. They're all there for us to use. So if I were to take, let me just do a C chart very quickly. How many samples? I'll say I have 5 samples. We'll just call it typos. Alright. And let's call it C chart. CCHART. So if I do this, it is so easy that we literally have practically nothing to do. This is too easy for words. So let's just put defects. So I got 5 defects. And another great use of this is complaints per week, customer complaints. So let's see a complaint as a defect. We could say we have 5 complaints for week 1, 10 complaints for week 2, 3, 2, and 6. So here's what we got. So if you look at this, these are defects. So the defect rate is 5. That seems to be the average, I guess. Standard deviation is 2. The Z value is 3. Total number of units sampled is 5. So let's see upper control limit, center line, lower control limit. Let me just open this up a little bit. And here we go. So if we were to look at a graph of this, here's where our values are. And we could 1, 2, 3, 4, and they're all within the control limits. It would be nice if we could actually plot those things, do a line graph through there. So the process is in control. We have no big issue with that. But what if we all of a sudden got 20 complaints in a follow-up week? Then we have to say, whoa, why did we get 20 complaints? Something must be wrong. Perhaps we had a bad batch of product that we sold to customers and they were all complaining at the same time. So that could certainly be a potential explanation for that. Okay, so I just want to demonstrate the C chart, the P chart, X bar chart, and so on would all be quite similar. All we have to do is to have the data to enter into XLOM, and life is a whole lot easier after that. So the last thing on statistical process control that I want to talk to you about is a concept called process capability, which is that because the output from a process is random, if we're thinking about a manufacturing process, sometimes we wonder whether or not the process is capable of delivering according to some specs. So let's just say this is the output from the process. What may happen is that we could specify what we call tolerance limits. So this is a target that we want to achieve, and then we have what we call an upper tolerance level and a lower tolerance level. So usually we'll have the target plus or minus a tolerance. Example, 5 plus or minus 2 centimeters means that we're willing to accept between 3 to 7 centimeters, right? If we add and subtract those two things. So what happens is that we sometimes want to know whether or not our process is capable. Well, if it so happens that the range of the process is within the tolerance limits, then we're cool. Then chances of producing defects are relatively small. But what if this extends outside of the limits right here? Then what if our tolerance limits actually were here, right? What if our tolerance limits were here, and this was our lower tolerance and upper tolerance? Then in that case, anything beyond that point would be defects because they exceed our tolerance limits. All right, and so we would have a certain percentage of defects that we're producing from that process. So how can we measure that? We have a measure for what we call process capability. Okay, so process capability, oops, and we call it CP. So what we do in this case is that we expect for a normal distribution that most of the values to be within 6 standard deviations. All right, 6 standard deviations. So if we take the upper tolerance limit and subtract from it the lower tolerance limit, that's the range. If we divide that by 6 standard deviations, then that's the process capability, and we expect that to be greater than 1. The larger it is, the better the tolerance. If it's less than 1, then we have an issue with producing defects. We have a certain defect rate. Now, you know, this we could get this measure greater than 1, but we could still have a problem. Let's see why. What if we had tolerance limits like this, but our process sort of looks like that? Now maybe the range here for this process is smaller than the overall tolerance limit. So this is our upper tolerance limit, and this is our lower tolerance limit. What happened is that on this side we have no issue with creating defects, but look at that. All of a sudden there's the risk of all of these defects. So what we do is we want to consider this possibility that even though the total range of your process might be smaller than the range of your tolerance, but because the process may not be centered, because this may be the center of our target right here, but this is the mean of the process. So you can see there's a difference between the mean and the target. So in a case like that, we redefine now our process capability as CPK, which is the minimum. And what we do is we take a left side tolerance and a right side tolerance. So on the left side, we will say it is the mean minus the lower tolerance limit divided by 3 standard deviations. So now we're only going to consider half, or the upper tolerance limit minus the mean divided by 3 standard deviations, and we'll take the minimum of those two. So if you look at the case of the right side tolerance for this here, I think we'll be looking very, very good, right? Because the 3 standard deviations from here to here, that 3 sigma is a lot smaller than the difference between that mean and that upper tolerance limit. So this part is going to be very large. However, the bottom part is not going to be quite as large. So our process capability is limited by the smaller of the two. In ideal cases, you want both of those to be greater than 1, so that your CPK, of course, would then be greater than 1, in which case your process is highly capable. So it's kind of useful to know how to measure this, and the calculations are fairly straightforward. If we were to go to XLOM, we could certainly do this. Let's see how we could do that. Let's go to quality control, process capability, and it's fairly straightforward. So title, process capability, sheet name, we'll call it PROC, PRA. That's okay. And what do we have? Let's widen that so we could see a little better. 20. So let's just say we have a mean of a process which looks like this. 30 centimeters. Standard deviation of the process, we'll use 8 centimeters. Alright? What's our tolerance limit? Well, let's just say our upper tolerance limit is 40 40, and our lower tolerance limit is 20. So what do we have? So if we look at this, 20 and 40. So the mean is 30. All right. I'm basically using a tolerance of 30 plus or minus 10. And as you can see, we don't have very good one side capabilities. And the overall process capability index is rather small. So which means we'll produce a lot of defects. If we would look at this, essentially 3 standard deviations is 3 to 24. 24 plus 30 is 54. So we would have to, first to get a process capability of more than 1, I may need something like 60 as an upper tolerance, or higher. Let's just use 60 as a upper tolerance limit. And then if I went down to a lower tolerance limit of, say, 0, then all of a sudden I'm at 1.25, as you can see. All right. So the mean is still 30, but I have a much wider tolerance now, and so my process capability is pretty good. So there's a pretty good chance that I would not create any defects with this process. All right. So all we need to do is to know our tolerance limits, our mean and standard deviation of the process, and we could compute those. And for now, as you could see, our capabilities are greater than 1, so the chances of creating defective items are rather small. Okay, so that just gives us a little summary of statistical process control. There is the topic of inspection that we've decided not to cover in this course, but certainly if you have an interest, you could continue to read that in the text.